Unit 2 Magnetostatics Lecture 1_1. Today we will take up Unit 2, that is Magnetostatics. Now what is magnetostatics? Magnetostatics is the calculation of magnetic fields and magnetic flux densities produced by different types of steady currents. Steady currents means DC currents. Now these currents are basically of three types. First are line currents or filamentary currents. The second are surface currents. And the third are volume currents. Actually, line currents and surface currents are approximations of volume currents. Next, in the last unit, that was on electrostatics, we had seen that there were two basic laws which we used to calculate the electric field and the electric force between point charges. The first was Coulomb's law. Coulomb's law is a general law which applies in all cases irrespective of whether symmetry is present or not. On the other hand, Gauss's law is a special case when there is symmetry in the problem. The advantage of using Gauss's law is that a lot of the integration associated with Coulomb's law is avoided. Now, exactly in the same way, in magnetostatics, we have two laws. Biot-Savart's law is a general law which applies to all cases irrespective of whether symmetry is present or not. On the other hand, Ampere's circuital law is a special case when symmetry is present in the problem. The big advantage is that a lot of the integration associated with Biot-Savart's law can be avoided. We now take up Biot-Savart's law. This law states that the differential magnetic field intensity dH produced at the field point P by a differential current element IDL located at the source point A and oriented along the direction AB is proportional to the product of IDL and sine alpha, where alpha is the angle between AB and AP, and inversely proportional to the distance r between the source point A and the field point P. In vector notation, this is represented by equation 2.1, which states dH vector equals I dl vector cross AR vector divided by 4 pi r squared. Here AR is the unit vector along the direction AB. This can also be stated as I dl vector cross r vector divided by 4 pi r cubed, since AR is given by r vector divided by r vector magnitude. Now the magnitude of dH is given in equation 2.2 as I dl sine alpha divided by 4 pi r squared. Now, having stated Biot-Savart's law, we must now find out how to apply this so as to evaluate the field dH due to IDL. The first stage is to calculate what is dl vector. Now, dl vector is given in equation 2.3. It can be expressed as magnitude of dl that's the length of the element, into AL vector, where AL vector is nothing but the unit vector along the direction of DL, that is in the direction from A to B. Now, let us assume that A has Cartesian coordinates x1, y1, z1. B has Cartesian coordinates x2, y2, z2, and the field point has coordinates x3, y3, z3. Then we know that dl will be written as dl magnitude into x2 minus x1 ax vector plus y2 minus y1 ay vector plus z2 minus z1 az vector divided by under root x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared, as given in equation 2.3. So we can now say that dl is expressed as dlx ax vector plus dly into ay vector plus dlz into az vector, where, as we know, ax vector, ay vector and az vectors are unit vectors along the x, y and z directions. Now dlx, dly and dlz are given in equation 2.4. dlx is dl magnitude into x2 minus x1 divided by the magnitude of the vector AB, which is x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared, whole thing under root. Similarly, dly is given by dl magnitude into y2 minus y1 divided by the same magnitude, and finally dlz is given by dl into z2 minus z1 divided by the same magnitude. So with this we have obtained what the vector dl is, and of course idl will be I multiplied by all these things. Now this slide tells you how to get the direction of dh. As we saw from Biot-Savart's law, dh is dl cross ar or dl cross r. So the direction of a cross product is given by the right hand rule or the right-handed screw rule. Also, the standard notation for a vector, any vector, when it is coming out of the paper towards us is a circle with a dot, whereas when the same vector is going away from us into the paper, the notation is a circle with a cross. Now coming back to the Biot-Savart law, we have earlier calculated what IDL is. We now have to calculate what is r vector divided by r cubed. This is given by equation 2.5, which states that r vector by r cubed is x3 minus x1 into ax plus y3 minus y1 into ay plus z3 minus z1 into az divided by r cubed, and r cubed is nothing but x3 minus x1 squared plus y3 minus y1 squared plus z3 minus z1 squared, the whole thing raised to 3 by 2. And it also can be written as rx into vector ax plus ry into vector ay plus rz into vector Az, where Rx, Ry and Rz are given by equation 2.6 as Rx is x3 minus x1 by x3 minus x1 squared plus y3 minus y1 squared plus z3 minus z1 squared, the whole thing raised to 3 by 2. Ry is y3 minus y1 divided by the same denominator, and similarly Rz is z3 minus z1 divided by the same denominator. So we have calculated what is IDL and what is R vector by R cubed. The next step is to calculate their cross product. Now we know from vector algebra that A cross B can be written as a 3 by 3 determinant where the first row is Ax vector, Ay vector, Az vector. The second row as capital Ax, capital Ay, capital Az, and the last row as capital Bx, capital By, capital Bz. And when we expand it, it is given by equation 2.7 as Ax vector into Aybz minus Azby plus Ay vector into Azbx minus Axbz plus Az into Axby minus Aybx. Applying this formula to our case, where we have to evaluate I dl cross r divided by 4 pi r cubed, we get dh as represented by equation 2.8. So dh is I by 4 pi, determinant, first row Ax, Ay, Az, second row dlx, dly, dlz, and last row Rx, Ry, Rz. dlx, dly, dz as well as Rx, Ry, Rz have been obtained earlier above. And this can be expanded as dhx into vector Ax plus dhy into vector Ay plus dhz into vector Az, where dhx, dhy and dhz are the components of vector dh along the x, y and z directions. Now the values of dhx, dhy and dhz are given in equation 2.9. dx is dly rz minus dlz ry whole bracket into I by 4 pi. dhy is dlz rx minus dlx rz whole bracket into I by 4 pi. And finally dhz is dlx ry minus dly rx whole bracket into I by 4 pi. So we have now found out how to actually implement or how to actually evaluate Biot-Savart's law. In an actual numerical, which will be taken up later on, the coordinates of A, B, C would be given, the value of the current I would be given, the value of the element dl, that is the length of the dl, small element, would be given, and we would be asked to find out the field at point P, the field point. Now in the beginning, we had said that in magnetostatics, there are three types of current distributions, namely line or filamentary, surface, and volume. Now, we have seen how Biot-Savart's law can give us the magnetic field due to a differential line current or differential line element. Therefore, the complete total magnetic field will be nothing but the line integral of I dl cross AR vector divided by 4 pi r squared as stated in equation 2.10. And this line element is shown in figure U2_4a. Next, we have a surface current which is shown in figure U2_4b. Now the surface current is represented by k vector into ds. The direction of the current is given by the direction of the vector k. So the total magnetic field produced by a surface current would be given as the integral of k ds into AR vector divided by 4 pi r squared, and this of course would be a surface integral. This is given in equation 2.11. Finally, we come to the volume current shown in figure U2_4c. So the volume current is always represented by J dV, where J vector is the volume current density. So the magnetic field produced by a volume current would be volume integral of J vector dV cross AR vector divided by 4 pi r squared as stated in equation 2.12. So these three formulae for line currents, for surface currents, and volume currents will be used in the subsequent slides to evaluate the magnetic field produced by different configurations of currents.